calculus, people freak out about it. It's really not all it's cracked up to be. It is very doable. You just need to not freak when you see the word. Okay. One of the areas of calculus is differentiation. Okay, so if you're asked to differentiate an expression, bless you, you will end up with what we call a derivative. Okay, so all of these words sound very fancy, but do not stress. Now, calculus is the big umbrella part. There are lots more elements to calculus, but we just look at differentiation in GCSE. Okay? What's it all about? Well, when asked to find the gradient of a straight line, okay, we know that we can just look at the rise over run. Yes? We would find 2 points. Okay, either the two red parts or two blue parts, but we would establish two coordinates. We would find the rise and the run, and we would do rise over run. So what is the gradient of this line?
2.
Yep, it's 4 over 2, which is 2, or 2 over 1 if you were looking at the blue one, yeah? Easy. It's just a one value. So that's fine. If we were asked to find the gradient of this function, can we do that? Can we just find the rise over run, this curve here? No? Why not?
It's not a straight line.
It's not a straight line. So my gradient is different all over it, yes? So if I were to say, right, what would the gradient of the graph at this position be? It would be different to the gradient at this position, yes? Now, when I say the gradient, what we're doing is we are looking at the tangent drawn to this curve. Do you remember what a tangent is? We just looked at tangents when we looked at circles.
It's like that, the line.
A straight line, yes? And it just touches it. Perfect. So here, a tangent to this graph at this particular point, we would draw a straight line where it just touches there. That's a rubbish straight line. But that's what we could do. We could draw a tangent, and we could then actually measure this amount, and we could do our rise over run. Yes? So have I ever seen one of those? I don't think I have, but just to be aware, just in case they ever ask you to, on your graph, show a way that you could find the gradient, you could draw a tangent, and you could draw a little right angle triangle, and you could measure your rise, your run, and you could do one value divided by the other. What can we see about this tangent? What kind of line is it? And I know it's a straight line. I'm sorry, it's gone way back there. It's a straight line. What kind of gradient does this line have? Positive. It's a positive gradient. Is it a big number? Is it a small number? What's the deal?
Small.
Okay, sorry. Well, I shouldn't say big, small. Is it is it a fraction? Is it a whole number? Okay, so this is quite steep, is what I'm trying to say. Yes, it's not like this, which would be a fraction. Okay, so I'm not saying it's 700, but I'm saying it's more like 4 or 5 rather than 2/3. Yes, that's why I mean difference between big and small. If I were to take this point of the graph and I were to draw a tangent, what do we know about the gradient there?
Negative.
It's negative, yes? Okay? How about this point here? If I were to draw a tangent, it would look like this, yes?
Mm-hmm.
What do we know about the gradient there?
Fraction.
It's 0, yes? It's horizontal. So the gradient of that line would be horizontal, which is 0, yes? But as you can see, it changes all the time. Yep.
How do you know how long this is on?
It shouldn't matter, because and that's why I did both of these two here, because my rise and my run here ended up at the same value as my rise and my run here. So as long as it's drawn as a straight line, it doesn't matter how long. Now, as I say, actually using this method is few and far between in the exam. Okay, so it's unlikely you will be asked to actually do this, but just in case. Okay, we have to do a few things just in case. So, I talked about this point what the gradient was at this point and this point. Now, these points are all relating to the value of x that is attached to it. So we would say, what's the gradient of the function when x is this value? What's the gradient of the function when x is this value? What's the gradient of the function when x is this value? Yes, you okay? So it's always talking about the value of x and the gradient of the function at that point. So this, very tedious. So what we tend to do is we want to try and find an expression that's going to help us. Okay? So in these cases we'd use calculus to find an expression to tell us what the gradient would be for any given value. This is called the derivative. Okay, so the expression that we're going to have is called the derivative. Okay, so you need to put that word in, the derivative. If they were then asked to find the gradient at the specific value of x, we can then substitute the value into the derivative and find the numerical value. Okay? So, how do we find this derivative? Well, it's actually pretty straightforward, she says. So finding the derivative will allow you to calculate the gradient at any given value for x. The rule for differentiating is multiply by the power and take 1 off power. Okay, so you multiply by the power and then you just take 1 off. Pretty straightforward. So if my function, if my expression here was x cubed, okay, so the graph I've drawn is just y is equal to x cubed, my derivative would be what? I've said that I have to multiply by my power. What's my power?
3.
3. So where do you think that 3 is going to go? When we haven't anything to be multiplied, then we go to the front, yes? So it's going to be 3, and then it's going to be x. X has to be involved somehow, and then we take 1 off the power. That's it. So it's going to be 3x squared. We have just differentiated this expression. Okay? Power comes into the front, so we multiply by the power, and we take 1 off the power. That's all you have to do. Okay? We show the derivative in 2 different ways. So here my expression said y equals, okay? So if I wanted to show someone else that I had differentiated it, I would write dy dx. Okay, so if my expression was y equals, my derivative would be called dy dx. If my expression here had said fx equals, which it can do, okay, the rule for differentiating is exactly the same. It's just we label it in a slightly different way, and this would be f dash x. Now, you may or may not recall, when we talked about inverse functions, how do we show an inverse function? Good, f minus 1x, okay? These two look similar. So in an exam, if they've asked you to find f dash x, make sure you're differentiating. If they've asked you to find f minus 1x, make sure you're finding the inverse, okay? So just be aware that these look similar, but they are completely different, okay? And if all the question says find that thing, then it's easy to get confused, so try not to do that. Okay. Well, that first one was really straightforward. If there's a number in front of the x, okay, it has no effect on our process, but what it does mean is that when we are multiplying by our power, we're going to have to take this 3 into account. So here, my dy dx would be 5 lots of 3x to the power what? 4. Pretty easy. Do you think we would leave it like that? What would we write? 15x to the 4. Now obviously my working step of the 5 multiplied by 3x to the 4 is because these are our notes. There are examples. You do not have to show this step. You can go straight to the 15x to the 4. Okay? If there's more than one term, you're just going to use this rule repetitively for each separate term. Okay? So y equals x to the 4 minus 2x cubed plus x squared. So dy dx would be, what's the first term? 4x cubed. 6x squared. 2x. Okay? Are we all thinking, what's the big deal about calculus? Exactly, which is what I was trying to tell you. There are a lot of aspects to calculus which can make it more complicated, but the general process of differentiating is a very straightforward rule. You just keep following the rule. The numbers may get trickier, but the rule is the same over and over again. Okay. If you're trying to differentiate something with just a number and an x, okay? If it was y is equal to 8x, my derivative would just be 8. Now, let me just go through y. If we have y equals 8x, I'm going to write y equals 8x to the power 1. Okay? We don't normally write to the power 1, but it's there. So dy dx, following our normal rule, would be 1 multiplied by 8x. And what do we do with this? We subtract 1 from it, yes? So it now becomes 0. Well, what do we know about anything to the power 0? It's equal to 1. So then we've got 1 multiplied by 8 multiplied by 1, which is obviously just 8. So if you ever have a term with just a number in front of the x, the derivative of it will be the value in front. So if we've got y is equal to 3x, my derivative is 3. Y is equal to minus 5x, my derivative is negative 5. And so on and so forth. Okay? When differentiating a constant term, so a constant term has no x attached to it, okay? Oh, I don't know what's that. Is your 4 randomly over here as well? Yeah. Can you just put it on here? I don't know what happened to that. Okay, so when differentiating a constant term, the derivative is always 0. Okay? We are differentiating with respect to the x value. Okay, so if there is no x attached to it, it means the value is 0. So if I were to differentiate this function here, firstly I need to spot that it says fx this time. So how do I show that I'm differentiating? F dash x. So this term has got an x, so this 5x cubed would be 15x squared. This one's just got an x, so we know it's minus 2. And this just disappears. Okay, the plus 4 has no x attached to it, therefore it's just gone.
Why did we minus 2?
Because we had minus 2x, and we just discussed that if there's a term with just an x, 1 should be x. No. Minus 2x, the x just disappears. So that's where the minus 2 came.
Oh, just not, and then you have...
And the 4 is a constant term, which is always 0. We never write plus 0.
Why is 4 0?
We just said that here. We're differentiating a constant term. Something that has no x attached to it is always 0. Okay? Now, here's a tip for you. I have seen many students that would have this expression. They'd differentiate these two, and then they'd accidentally write +4. And then they'd say, oh, hang on a minute, I've got to do some simplifying. I can join my like terms. I've got 15x squared + 2. And be very happy with themselves, and off they trot. If there is a situation where you would end up joining like terms, you have made a mistake, okay? Because if I look at this expression here, can I join anything together? No, there are no like terms here. Therefore, for my derivative, there would be no like terms either. Okay, so if for some reason you have a like term, you've done it wrong. Okay, so that's something for you to try and remember when you're doing these things, is keep an eye out. If you end up simplifying, it means something's gone wrong. Now, because we know the processes that we take one off the power, you should have noticed each time this was a cubed, ended up as a square. This was an x, it ended up as a number. Your powers will always decrease by 1 each time. Okay, so this was a cubic expression. This one is going to be a quadratic. Okay, so that's always going to happen. We start to get into the slightly more complicated zone. We might have a negative power. Okay, the rule is exactly the same though. The power goes to the front and we take 1 off the power. The thing that you have to remember here is that when you subtract 1 from -3, it becomes -4. Okay? So that's something that some people make mistakes with. So y is equal to x minus the -3 would be -3x to the -4. Again, not stressful, the same rule. Nothing has changed whether it's negative or positive. The challenging thing comes in that it's not always going to be written like this. Okay? It may well be written like this. So if it's written as a fraction, you need to deal with it first of all. Now this is going back to laws of indices that we've done in the past. If you've got y is equal to 1 over x to the power 4, that would be rewritten as what? Good. Okay. Now, I have just rewritten my original question. I have not started differentiating it yet. So I was able to just write equals because these two things are equal to each other. If I were then to differentiate, I would then have to show that I am differentiating, so I put my dy dx there. Now my fraction is in index form with just my power next to it. I can use the rule. -4x to the power -5. They should not expect you to go back to the original format. It used to be a situation in the past that they often would, but they shouldn't be requiring you to go back to the original form. But if they did, remember it's just the x that is to the power of -5. So if I were to rewrite this, this would be -4 over x to the power 5. Okay, I'm going to put that in brackets to remind you that that's not usually essential to do that, but just in case. Okay, so the x is to the power of -5, so that's the thing that goes back underneath. My -4 stays on the top. Okay, you all remember that? Whoa, so much love.
So that x5?
It does say x to the power. All right, 1 over x squared. Well, how would I rewrite that?
X to the -2.
X to the negative 2. So dy dx would be -2x to the -3, which would be -2 over x cubed. Four over x cubed. Yeah. So dy dx is equal to
X.
yeah, that's right. One over 3x squared. No,
3x minus 3.
no,
6x.
no.
Negative
What did we say up
3.
here? Why did the negative 4 stay on the top? What was raised to the power?
Oh,
So it's just the x that has the negative power, yes? Okay, that's why the 4 stayed where it was. So down here, it's just the x that has the power, yes? So this would actually be 1/3 x to the negative 2.
Why?
Because the 3 has to stay where it is, it has to stay underneath of the fraction. If it had said this, that would be 3x at negative 2. Okay? What do you mean why?
Like, why? How come?
Because here it's just my x that has a power of 2.
How come they documented without that?
I mean, when I say it can't move, it could move, but you would write 1 times 3 to the negative 1, x to the negative 2. Okay? Because this 3 and the x are separate. Whilst they're next to each other, they're being multiplied. They don't act as one term. Okay, these two things, it's not 3 squared. 3 is not, there's nothing to do with that power. So ideally you leave it where it was on the bottom of your fraction. So if you go back to our index notes, you'll see that we've got a few of these. So if you have a number on the bottom, you just leave it on the bottom. Okay? But that's okay? Okay? So if you've got numbers on the bottom, be careful. Differentiating this. Well, now you've got to do negative 2 times 1/3. Negative 2/3, yeah? X to the power of negative 3. In a similar vein, if we were to then put the x back underneath, you just put it next to the 3. So, again, our bracket section would be negative 2 over 3x cubed.
How come they say the x cubed in the bottom? When you rearrange it.
So in every single one of these, the bracket is the optional stage of just putting it back to where it was. So here I had a negative power of 3. So I could rewrite it with that term on the back on the bottom, and that power then becomes positive. So if you remember the index laws unit we did, that we had sometimes it said write as a positive power. So if we did have something like this and we had to write it with a positive power, we would just put it underneath. Okay, so it would always go underneath in the denominator of the fraction. Does that answer the question or what? Yes. So once you've rewritten the expression, so that's what we did first, then obviously you differentiate as before. Okay, let's do some of these. So my suggestion to you is before you start differentiating, you need to look at the question. Is there anything that needs rewriting here? Helen, Heather? The fraction, yes. Okay, so so first of all, we're going to just rewrite gx. Notice I haven't changed it to the g dash yet. So my x cubed is as it is. What am I going to do with that other term, the fraction term? Layla, how would I rewrite it?
The dy dx.
Not yet, I just want to rewrite this term here with the x not on the bottom, because I can't differentiate it when it's on the denominator of a fraction. So what happens to it when it's underneath a number?
You would do 3x to the power of -2.
Yes, awesome. Okay. Now, I don't want to say this to confuse you, but again, I have seen it too many times. Please don't start differentiating, okay, until it's rewritten. I've seen too many times people will differentiate this part and rewrite this part and then differentiate everything again. Okay, so don't get yourself mixed up. Look at your question. Does anything need rewriting? Yes, so I've done that. Then go on and differentiate it. Okay, don't mix up the processes because you're just going to get yourself really mixed up. So it was gx, so to show I'm differentiating, I'm going to write g dash x. Jodie, what's my first term going to be? Nice, thank you. Samantha, what's my second term going to be?
-5x.
Careful. How did you get -5?
-6x.
Yeah. Is that it?
Power of -3.
Nice, awesome. Who said that? You did. But Samantha, you tell us, how did you do it?
You times the number in front with 3 by -2. Right down.
Yeah.
Wait, what about the x3? -1. -2 minus 1 is -3.
How did you get straight to it? Jodie, back to you. You did this one.
You multiply the x by the ABC.
It's the process we've just been doing, sweetheart. So the power
Oh, right.
gets multiplied,
Yep. And then
and you take one off.
And then for the others, then
Same
you
method.
did. Oh, you did do that.
Power multiplied,
And then x.
take one off that. Okay? Yes? Okay, next one. Is there anything that needs rewriting? Yes, Elaine, how am I going to rewrite this up?
The first one stays the same. Second one stays the same.
Yeah.
And that one,
Which part's raised to, which part has a power attached to it? Okay, so where's the two?
it would be x to the -2 divided by 2.
Yeah, so it's easier to leave just that there, yes?
Okay.
And then x is -2. So if you want to, when you've got these, maybe just circle it and see what we've got left. So we had the -3/2, yes? And then my x became -2. Are you all happy with that? So I haven't differentiated yet. I haven't started doing anything. I've just rewritten it. Now I'm going to differentiate. So now I show g dash x. Ashley, what's my first term?
6x.
Nice, 6x squared. And Emily, what's my second one? What sign am I going to write?
-2.
Yep, -2x. Amelia, what's my next one? Pardon? What happens when there's just a number? Pardon?
Goes to 0.
Goes to 0. I've just pulled a big chunk of my hair out. So, shall we write +0 just for the crap? Just so we remember that that's where it came from? But obviously in real life you probably wouldn't write anything, okay? But seeing these are our notes, we're just going to write it in. Aria, what's my next one? Be careful. What sign does it have in front of it? Yeah, so we've got negative 3 over 2 multiplied by negative 2. If you're rubbish with fractions, you have calculators available to you in your exams, okay? But negative 3 over 2 multiplied by negative 2 gives us positive 3. Nice. Okay? And that's my final answer. Obviously, you probably would rewrite it without the 0.
What is your last one?
Okay, so we had negative 3 over 2 multiplied by negative 2. Yes, you happy with that? So, just looking at that part, the negative 2 is equally negative 2 over 1. Yeah, top times top, bottom times bottom. So that's positive 6 over 2, which is 3.
So how did you get the negative?
Because we took 1 off the power. Yeah, so this part here was just giving us this 3. Okay, but as I said, you've got your calculators, so you can just chuck that bit into your calculators if you don't want to do this by hand. They're not going to expect to see this by hand. Okay, when they're allocating marks, it's sometimes a term by term basis, so that you get perhaps one for each of these terms. Sometimes if there's several, they may deduct a mark for each mistake you make. So just try and avoid making too many mistakes. Okay. Things like this. Again, it's always tricky to know whether they're going to come up or not, but I wanted to go through some just in case. If you have anything like this, both of these two terms have a denominator of 3x. So if you have something that looks like this, what you need to do is you need to split it, first of all. So this expression here would be split by having 6x squared over 3x minus 9x to the 4 over 3x. Okay, so all I've done is I've taken both terms of the top. I know that they are both having the same denominator, and so I've just literally split them, writing that same denominator for both terms. Okay? Well, before I start doing anything, I need to try and simplify it if I can. So I've got 6x squared over 3x. Hopefully you can see we can do some simplifying here, yes? So I've got 6 over 3. So what is that going to become? 2. And I've got x squared over x. It's just going to become x, yes? I don't think I will show here. So this is a 2 and a 1. This is a secret power of 1. So we've got 2 subtract 1, which just gives us 1. I don't know if that makes you feel better. But because I had just 1 on my denominator now, I don't need to write anything on my denominator. Similarly, we've got 9 over 3, so that's going to be what?
3.
Yeah, so that's going to be 1. And then x to the 4 over x to the 1 becomes what? X cubed, nice. Okay, so we've simplified our expression, now we can differentiate it, okay? Oh, I haven't called it anything, let's call it y. Okay, so each of these steps we're just rewriting my original question. Now I'm showing I'm differentiating. So if it's just 2x, my derivative is, Jersey?
2x. 2.
Just 2, yep. Okay, so whenever there's an x, it's just the number in front of it.
Wouldn't that be y dash?
No, so when it's y, we write dy dx. If it was fx, that's when we write f dash. And Hannah, what was my next one?
-2, -1.
Pardon?
X squared.
Nice. Okay? Just the ends? Right. Ooh. Okay, why am I oohing? There's a root. Okay? So, again, we need to go into the depths of our remembrance about indices and roots. How would I rewrite? This is a big 4, not a root 4. So it's a big 4, so my 4 is going to be there. How do I show the square root of x as a power? Amy, do you remember that? Oh, it does, sir.
X to the power of a half.
Oh, my giddy aunt. X to the power of 1/2. What? They have been studying. Okay? Let's sidestep slightly. If it had said cube root of x, what would we have written? Yeah. X to the power of 1/3. If it had said fifth root of x, it would have been x to the power 1/5. Okay? Recollection of that, Bacon? Okay? So, because this was the square root, it was to the power of 1/2. Yeah? So I've just rewritten my expressions. Let's call this y then. So now I've rewritten it, it's as a power, I can do my differentiation. So dy dx. Oh, here we go. What's 1/2 multiplied by 4? Oh, nice. Now, here we go. We've got 1/2. What do we have to do to our power? We subtract 1. Okay? We're not subtracting 1/2, we're subtracting 1 whole 1. So what's 1/2 subtract 1?
-1/2.
Nice, negative 1/2. Okay? And then we've got plus x. Okay, what did we say when there's just an x? It's just going to be the value in front of it, the coefficient of it. What secret number is in front of this? So it's going to be a plus 1. Did you say 2? Were you tricking or were you serious? What have I then? Okay, so we are going to stop just there.